Hello, Flat Earth researchers, debaters and debunkers. This is the second in a series of videos on how to navigate across the flat Earth or across a level Earth by using celestial navigation. Basically, we are looking at how the imaginary globe was created as a projection for navigation and how observations have been interpreted into distances across the Earth. So hopefully what you'll gain from this particular video is that angles are converted into distance. Angles equals distance. This is the fundamental trick that is used to create an imaginary globe when we are making observations across a level Earth. So let's just turn this around to do a practical demonstration. Alright, so here I am on the Earth's surface, and you can see on the corner of the table there an incense stick. So of course, as I get closer to that incense stick, the top of it gets higher in our horizontal field of view. We're on a level surface here, and the camera is pointing in a horizontal direction. And this is really very similar to how sextants work. So if you consider that the top of this incense is a light in the sky, could be the sun, could be Polaris, and we'll see that, of course, the closer we get, the greater our angle increases to put that tip in the center of the field of view. Okay, this is reality. This is how it works in reality. And of course, as we get further and further away, the tip gets closer and closer to the surface. So it gets closer to our horizon. So, let's just assume that this is what's actually happening. So what we have is a distance that is that relates to an angle of declination. Of course, if we were directly underneath this, if we were sitting on that plasticine blob at the bottom, which we would call the ground point, or the GP, the ground point, that is the point directly below the light source, regardless of how high you imagine or calculate that light source to be. Okay, so in this sense, you've got your 90-degree angle. You've got your vertical going up, going straight down to the ground point, and then you have this horizontal plane that we're going across with an ever-changing angle to the tip of that incense stick, or our light in the sky. Okay, so that's how it works in reality. In reality, when we make an observation of something in the sky, the further away we get, the lower in the sky that will appear to be, or the closer to the surface it will appear to be. All right, so how do we then measure this distance? How does it all work? Well, let's turn to the whiteboard. Just give me a second and I'll hook this up. All right, so let's just translate the setup we saw on the table just now, where we had a point of light in the sky. Could be the sun, could be Polaris. Let's consider this Polaris as the North Pole for the purpose of talking about latitude and declination. They are the same thing. In celestial navigation, latitude and declination have the same definition. Okay, so your latitude is the distance from the North Pole. Okay, and we know that that is the same as the result or the reading that you get at any given location that is a certain distance from the North Pole, or what's assumed to be the ground point beneath Polaris. Okay, this, you know, the actual real distance to being under Polaris might in fact be a lot greater. There might be a lot more space there before you ever get to be directly under Polaris. This is just an extrapolation, because I don't think anyone really went there to look up and start that navigation right there. You can just create it from the calculations. So latitude is declination. So as we saw just now, the further away we get from the ground point directly beneath this light source, the sun or a star, whichever star you choose, then the further away you get from it, the lower that star will appear to be, according, you know, depending on your distance. Okay, so this angle here will go down, just as we saw just now. Okay, this is very easy to understand, very simple, and it represents how we see things in reality, or how observations work. The closer we get to it, the greater our angle, until it's 90 degrees to this horizontal. Okay, this 90 degrees is also important. It's part of the calculations, and you'll see later on how this is used to create the mathematical illustration, but this is changed or ignored. The reality of it is ignored and converted into something else. So you have your 90 degrees of your triangle. You have a reading here, or a result that gives you, let's say, 24 degrees. Now this, when I say result, is not the actual angle. That doesn't mean that we are looking up at 24 degrees. It is the reading that you get, or the result that you get after doing some calculations based on this change that I mentioned and haven't, you know, we'll look into that later. Okay, so what we have is this 90-degree angle here, we have this angle here, so we can work out the distance, and when the reading is 24 degrees, the distance is 1,440 nautical miles. Okay, yes, you can convert that into miles or kilometers or any other number that you like, but nautical miles is used specifically for navigation because of this simple fact that 1 degree of latitude or declination is equal to 60 nautical miles. So we have a simple conversion here of an angle converted into a distance. And it's a distance that's easily manageable and calculable when we do 1 degree equals 60, 1 equals 60. Okay, so here we've got our reading of 24 degrees, and we multiply that by 60, and we get 1,440 nautical miles. We now have this distance calculated from an observation that converts the angle into a distance. Angle equals distance, okay? Angle equals distance. So this principle gives us a distance from our center. We've made this ground point beneath Polaris the center of our maps for latitude, okay? Which, you know, with the common flat Earth equidistant, whatever they call it, azimuth projection from the North Pole spreading out, okay, that is based on the same thing, because you've got this center point that's been decided upon as being the North Pole, and from then on you can do your measurements. Now longitude, okay, so basically this can end up giving you a circle. You could be anywhere on a circle around the North Pole. So, of course, just knowing your latitude doesn't help tell you which side of the Earth you're on. Are you on the west or the east or the north or the south? Well, sorry, yeah, the east or the west side. Where are you really? All you can do from latitude, is to know the distance from a center point. So you have the equivalent of a radius, and of course that radius can be, let's just draw this in. Okay, here's our center point. Okay, so this puts us on, we could be here, we could be here, we could be here, we could be here. At least we know that our distance, or the radius of this circle that we've created, is 1,440 nautical miles. Okay, so I have this. I know I'm that far away, but I don't know where I am. Apart from that, I know the distance from the ground point. So that's when longitude comes into play. But what they've done is they've used the same thing. Longitude equals time. And time, which is referred to as Greenwich hour angle, okay, it's just that, Greenwich mean time, Greenwich hour angle. So this agreed upon time to start everything off, Greenwich mean time, is called Greenwich hour angle. Okay, so again, we have an angle equaling a distance. The same principle is used for longitude. Yeah, it is a distance across a level Earth, or a level surface. It is this triangulated distance with your 90 degrees, your 24 degrees, and you've got your distance then. Easy to work it out. Yes, and you could then assume that the sun, or the source of light, is a certain distance based on this hypotenuse, yeah? Or however you want to say it, the hypotenuse, yeah? But of course, it's when you observe it, it has declined in your vision. It's not the actual height, is it? The only time you can actually get the actual height of something with an observation like this is when this is at 45 degrees. Okay, when the actual angle up is to 45 degrees, you've got a height and a distance across the surface here that's an equal length. Yeah? Because you can work out your length here. But that's not a true length, is it? It's not a tangible physical measurement, is it? Because the source of light, the sun or the star, is always in an apparent position relative to our position. So it's always going to be apparent. So yeah, it's not a physical measurement, but it is a measurement that is consistent with distance and angles, that we can then change the angle into a distance. And so when we talk about 1 degree, we are talking about 60 nautical miles. We're talking about this distance across the surface in terms of degrees. Okay? But it's still a distance. So, longitude is based on the same thing. It's simply turning an angle into a distance. And of course, if we represent time, we have our circle again. Yeah? And the circle is divided up into minutes and seconds and hours of time. And of course, it's 60. We've got these combinations of 60 again. Okay? Or, seconds, minutes, etc. are basically angles on a 360 degree circle. Yeah, so it's the same. Now we have this uniform way of converting angles into a measurement, or basically referring to a distance, angles into distance, or basically something that's established as consensus now, that X number of nautical miles is the same as X number of degrees on a circle. Remember, now we're talking about a circle that represents time. It's all imaginary. It's just an imaginary circle. for time. Yeah? So then of course what happens is you end up getting these, let's say this is point A and point B, and you're going to talk about how the different angles and distances between that. But we have to understand something else first about this 90-degree aspect of celestial navigation. And just before I go, the lovely stick person there, who's giving the angle reading, as was done by our resident artist Abigail. Okay, so that was she's helping me there and learning about celestial navigation, aren't you? Mm. So before we move on, we just look at this aspect of illustrating vertical parallel lines and the way that a line placed across those parallel lines will create very predictable angles. So this is the principle that is always true, that has been used when converting angles into distances to eventually give us this imaginary sphere. So you should know from lower grade mathematics that this angle here, we could say it's 30 degrees, for example, means that this angle here will also be 30 degrees, and it means that this angle here will also be 30 degrees, and this angle here will always be 30 degrees. So by using these two parallel lines, they could be vertical, they could be horizontal if you like, this principle has been used. So of course, if we then create some 90-degree angles around these areas, we put a horizontal there and a horizontal there, so we've got a perpendicular to the vertical, giving us our horizontal. And of course that gives us 90 degrees on this side, and it gives us 90 degrees on this side as well, all together. Okay, 90 degrees here, sorry, and all together we've got 90 degrees here. So it's simple enough to work out the angle that remains, isn't it? So the remaining angle here between the 90 and the 30 is basically 90 degrees minus 30 gives you 60 degrees, right? So we know from having one angle here that we can do all the other angles that relate to these parallel lines. So we've got one of these lines, make a parallel line, and you've got very predictable calculable angles. Okay, so this principle of having 90 degrees, a horizontal, perpendicular to a vertical, creating 90 degrees, and then being able to subtract whatever angle we read from 90 degrees gives us a reading. Yeah? So let's keep that in mind as we move forward. All right, I've had to move inside now, but let's now look at how to calculate the distance to the ground point, GP, with a sextant on a level Earth. Now, first of all, I want to point out a wrong assumption based on something that does work in reality, but is wrong when we come to making observations of angles of declination. So here you can see this illustration where we've got the surface and we've got our luminary, the sun or a star, and of course the further away you get from it across here, then yes, you do get a change in angle. But once you get past about 45 degrees, it starts to get you have to cover a lot greater distance before any significant change in the angle. It all just becomes mushed up, really. So yeah, this doesn't work. It doesn't represent what we are able to measure with sextants in reality. So people will say, oh, well, it doesn't work across a flat plane. But as we showed earlier, what we're actually doing with a sextant is what we observe happening when we get further away from something in the sky, and that is the declination. Remember, latitude is declination, and so we are going across a level surface as we are demonstrated, but now if you wanted to make these angles work, in this case, you would put a curve in, and all of a sudden you've got these angles which are more in line with what is measured. But of course, what they're not doing, the reason they put a curve in is because they're not doing this declination as we go a greater distance. This height of this, we're forming a triangle, so the height of this triangle remains the same, and they make the base longer and longer and longer and longer, and so it gets more and more difficult to get a smaller and smaller angle as you go off into the distance. But that's wrong, isn't it? Because nothing's changing. But what we are actually measuring is the declination. We are observing and measuring the angle of declination. So there is no declination here. So this is a wrong representation. But of course it does work in the real world with tangible objects, as I pointed out earlier. For example, we've got a building, and if we want to know the height of the building, then once we get far enough away to measure a 45-degree angle to the top of the tower, then whatever this distance is across here, this 200, is going to be the same height. So we've established these two equal sides of our triangle. We've got the right angle, and of course this again allows us to play around with it mathematically very easily. But once you go beyond 45 degrees, well, what's actually happening in our eyes? Let's say we go further away, then of course this building, I'll put it in blue now. This building is going to appear much shorter. Okay, its physical height hasn't changed, it's still 200, but to us it's going to appear much shorter. Just as we saw with the incense stick on the table, this is how it ends up working. So this again, this argument here is wrong. Of course it doesn't work, doesn't fit with anything really. But this, you can see, if we compensate for the declination of the top of this building as it shrinks in angular size, then of course we get a new angle, which might be something like, could be something like 25 degrees or something, yeah? Because we've got the distance. So that all works, and you can see that you don't have to go very far until this has come down to the horizon, and it's just part of the horizon, and we can make no more measurements. So again, that's what's happening in many senses with the stars or the sun, is that the further away we get, the lower it appears to be. All right, so that's that hopefully cleared up. Let me just pause it and put something else on. So let's just clarify what's been established so far with this conversion or equation of angles into distances, and the fact that we are playing with these 90-degree angles. So we have Polaris here above our North Pole, or the ground point on the Earth, on a level Earth. That's referred to as the North Pole because it's directly beneath Polaris. Whether or not anyone's actually been there and seen this doesn't really matter. We've got all these other angles that come down. So what we have either side, if we're looking at this just side on like this and seeing the same thing here top down, so this is side on and this is top down. And these are again just illustrations or interpretations, mathematical modeling if you like, of what we've established from the distances that we can associate with angles. 1 degree equals 60 nautical miles, yeah? So as we're playing with 90 degrees here, obviously
if you're looking directly up, then you're looking at this 90-degree angle here. But as we go down like this to 0 at the equator, let's just put that in there, 0 degrees meaning that Polaris has come down, 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 and appears to be level with the horizon, or is essentially obscured by the horizon. It's to that point. Boop. And so over here is 0 degrees as well. So this is established now as our equator or circumference. So of course, if you start looking up how was the globe first discovered or calculated or worked out, the size of the Earth, then of course they talk about circumference, whether it's Eratosthenes or whoever, working out that we have this circle here from the North Pole out to here that has a radius of 5,400 nautical miles, based on the distance of 60 nautical miles for every 1 degree of declination that we see. So now we've got this radius, we have our so-called R value established, 5,400 nautical miles. So this radius here is represented on either side here. Okay, so that has established for us 5,400 nautical miles from Polaris, from the ground point to here at 0 is what we have. And of course this can be represented as this kind of dome. We get the same angles, yes, whether you consider this to be a triangle or a sphere. What we have actually is this apparent dome above a level surface when we are taking these measurements. Okay, so of course what we then have is something that's easy to work with. So for example, let's just create another point here. All right, and then of course what we can do is, given that this line here is also 5,000 nautical miles, we have two sides of our triangle here. Yeah, and what actually happens is, by having this center point here, we then have an angle here that is going to also be exactly the same if we continue these lines, but we've got to do something else, and this is where the trick with parallel lines comes into play. So let's look at that next. All right, so here is our surface, and we are measuring angles to the star as we get further and further away. So HS means height sextant. Okay, so when we were here, we measured a height of the star, HS1, our first measurement, as 50 degrees. So that's our sextant measurement. So we just basically call it HS equals 50 degrees. That's the reading we got. So as we get further away on the level Earth, then we see this apparent declination of the star. So our second one, HS2, is going to give us a lesser angle to a star that appears much lower in the sky. So let's say about 20 degrees here. And then HS3, further away, then we've got a much smaller angle. That's how it works, as we've seen in reality, as we get further and further away. So let's just focus on this point here, HS1. So we are here, and we got a reading of 50 degrees with our sextant. So that's the degrees that we sight the star above our horizontal horizon. So we've got HS 50. Now this is where the parallel lines come into play, because we have a vertical line here going straight down through our ground point and then going all the way down through the earth just beyond us there. So in order to actually do the calculation to arrive at an angle that equates to a distance. Remember, what we're doing is we're finding an angle that gives us a distance. Angles equals distance, yeah? Based on this 1 degree of declination equaling 60 nautical miles. So what we have to do is we just now imagine another vertical line going straight through us, okay? And that gives us a parallel vertical. And this is why they now say, oh, the light from this star over here that we have measured as declining as we get further away is actually coming to us directly down. Yeah. So what they're doing is just transferring what's happening over here to also happening above us in order to give us this plumb, this vertical, which is a parallel line to that one. And then we've got something to work with. Again, this is just illustrating how the calculations are made. So now what we've got is because we've got this vertical and a horizontal, we have created our 90 degrees on this side, and of course it's 90 degrees on this side as well. Okay, but all we do now is subtract the 50-degree measurement that we got from the 90 degrees to get this angle here. And 90, so basically let's just do the calculation here. HS is 50, so now we take our 90, our vertical that we've created, and the horizontal, and we subtract the HS reading of 50, and that gives us 40 degrees. So this 40 goes here. Yeah, it's the difference between the 90 minus the 50. So what is this? This 40 degrees is now the equal distance. This is the degrees that represent a distance. And again, because 1 degree of declination equals 60 nautical miles, all we have to do here is multiply 40 by 60. Okay, 40 times by 60 gives us, I think it's 2,400 nautical miles. Yeah? 40 degrees is the same as 2,400 nautical miles. Yeah? Okay? Angle, distance, they're interchangeable. All right? So we now know that the distance between us here at our first measuring point, height sextant 1, and the ground point directly below the luminary, whichever one we've chosen, is 2,400 nautical miles. There it is. That's the distance across a level Earth. All right. But what we had to do was suddenly jump to this assumption that the light is coming to us in parallel lines. Whether it's a star or the sun, it's coming to us in parallel lines. So this 40 degrees, what does it really represent? I'll just pause it and I'll show you how that fits into the whole globe idea. So here's a circle, and here's a segment of that circle, and here's HS where we took our reading, HS1, and here's the ground point, okay. So we worked out that the distance across the surface from us to the ground point was 2,400 nautical miles. Yeah, so we can just put that in there, 2,400 nautical miles. So this you might refer to as a great circle distance, because we've got this 2,400 nautical miles, or 40 degrees, considered as being part of a circle that is equal to the circumference of the Earth. Now, as we said before, circumference can be just a flat surface, and of course that's considered the equator. So okay, whatever Eratosthenes worked out and whatever he considered the circumference is basically the circle of the equator, or a circle that is below the circle of the sun. Okay, of course it's understood that with a globe it's understood to be the girth of the globe, and if you have a completely spherical sphere with no bulges or pear shapes, then of course the equator is going to be the same all around anywhere you go, the circumference. Yeah, but so just keep in mind that what we're doing here when we calculate a distance, this is all we're focused on right now, not necessarily which direction we are heading. We're just talking about distance, and we've calculated 2,400 nautical miles across a level Earth. But in the mathematical model, we are considering it, this 2,400 or 40 degrees, as part of a great circle. Now, if you're navigating, you're never ever going to go that far. You're never going to go all the way around. You're only going to go from one point to another. And so these are just considered 2 points on the Earth. And so this isn't necessarily, again, it's often referred to as a slice through the globe. No, it's not. This isn't a slice of a globe. This is a circular, flat plane that has the same circumference as we said, whether it's the equator, basically, whether you consider that on a globe or a level Earth, it's the same. 21,600 nautical miles. Yeah, that's our circumference. Well, how do we arrive at that? Well, we're using this same thing again. We're doing 1 degree is 60 nautical miles. Okay, so to get at this figure, we can do 60 multiplied by 360, because 60 nautical miles is 1 degree, and there are 360 degrees in a circle, and this gives us our circumference of our imaginary circle. And it's just an imaginary circle that is the same as the circumference of the equator. And of course, again, as I said, if you consider that as being on a globe, you can think about it as a slice of a globe. But no, what we're actually doing in these calculations is we're not slicing through a globe. All we are doing is finding a way that we can equate an angle to a distance. So what of course we have here is this star above the ground point there, and this imaginary line going right down towards the center of this circle. Now again, people might say, oh, that's the center of a globe Earth. No, it's just the center of a circle with a radius that is equal to the radius of the circumference of the equator. So what's that? 5,400 nautical miles, yeah, if I'm not mistaken. 5,400 nautical miles. So we have this distance, yeah, because remember, all we're doing is we're playing around with tangents and angles and trying to arrive at a way that we can have this 2,400 piece of level Earth as part of a great circle. So then of course this line here is going to be the same. So again, what we did was we created this 90 degrees, yeah? We created this 90 degrees. So we have our vertical and we had the horizontal. It's done and dusted here on our level Earth. But in order to consider it as part of the globe, we just got to go a little bit step further. What I'm showing you really is how this fits in to the angle distance equation and how that is illustrated. So all we're doing here is we're not illustrating the shape of the Earth, okay? We are just illustrating how this calculation, how this equation how this degrees equates to a distance using 1 degree equaling 60 nautical miles, yeah? All right, so this again is going to be the same, this radius. So wherever that is, it's always going to be the same. So that's why we have this parallel line coming down here. And then of course, let me just change the color a little bit. Let's change it to red, maybe, no. I'll try and do black. So of course, what we had was a horizontal, and then we had our vertical. All right. This line here is this line here. Let's just call it A, okay? No, let's call it our V. Yeah. Yeah, we'll just call it vertical 2, okay? Okay, I'm just thinking about how we might... Okay, so vertical 2. Maybe this we can call our vertical 1. But, yeah? But our vertical here on a level Earth has now been put on a spherical Earth. Okay, so it's going this way. All right. So now we have to put the horizon like this. Yeah, because we were referring to vertical and horizontal, perpendicular to each other. So we have to recreate this perpendicular thing here on a sphere, on a circle. So then, of course, what you had here was your HS50 was your angle to the star. And again, this doesn't truly represent it because we are going to see declination, and that's what the curve is. The curve is basically representing the declination. That's all the curve is. Declination is curve, and over 90 degrees, you get, basically they've worked out how far can you get with 90 degrees of declination until Polaris hits the horizon. And that just takes you to the equator. And then beyond that, you're going to have to use some other measurements. Yeah? That's all this is. That's all this is fitting distances into 90 degrees of declination from underneath until so far away that it's reached the horizon. So then we've created our parallel lines, and so of course what we're getting now is parallel lines. Okay, so we've got this line, remember we looked at just now, okay, the parallel line. And so here we have our 50 degrees that we measured. Again, assuming that we're looking straight up at the star again. So it's 50, you see, the 50 degrees between this here that's imagined and the horizon is this here, this 50 degrees from the horizontal horizon here up to our thing here. And then this is the remainder, because we extended this line, our vertical from the center of a circle, we then get our 40 degrees here. Okay, and that's the figure we wanted to arrive at, because then this 40 degrees is the same as this angle here. This is 40 degrees. So that's how it all fits together, because what we've created up here is an angle that's the same as the angle going from these 2 points out to each other with a radius of 5,400 nautical miles, and giving us a distance across this part of the circle of 2,400. I can't remember what that was. 2,400. Yeah. Okay. That's it. So, yeah, this is just a case of fitting it in to a geometric model so that it's all in one place, and we can say, oh, right, well, 40 degrees is 2,400 nautical miles. Yeah, this is basically how you arrive at the correlation between the angles and the distances, because of course angles are part of a circle. Yeah, but actually it's then okay, this represents the equation, but this represents what we're observing in reality. Yeah, this is the reality of it. We see declination, we measure the difference, and then we create this imaginary 90 degrees, our plumb, And it doesn't matter whether you consider it to be on a level Earth or a spherical Earth, we still get the same result. Yeah? Degrees equals distance. Okay? So hopefully, I really hope that has made it clear. If it's not, then it's probably worth doing this again, because yeah, it took me a while to get my head around how it all works. But this is what we're doing. We are observing declination and equating that angle of declination to a distance. And that's what happens across a level Earth. But we are illustrating the calculations using geometry, circles, not a globe, just circles, because whenever you do one of these lines, all you're ever doing in navigation is measuring how far you want to go and the direction you want to go in. And it's done bit by bit by bit. Okay? Whether you consider the section that you're traveling on as part of a level plane or a globe makes no difference. Yeah, it's only considered spherical with parallel lines of light coming down in order to arrive at this degrees, which equates to a distance, nautical miles. Yeah. Hope that helps. Thank you very much.